All right, so we're going to go back to that Mountain Dew example. Remember, I rolled the dice. It was our talk about simulations and how we can use simulations to replicate situations and see if our simulation gives the same probability. So we're going to go back to that situation about the Mountain Dew giveaway. And we're going to learn how to use one of our rules in a new way. So it says, suppose that Mr. Wilcox is determined to win a prize from the Mountain Dew giveaway. Recall that the probability of winning for each bottle is 1/6. Assume each bottle is independent of the previous one. Mr. Wilcox buys 5 Mountain Dews. We want to find the probability that he wins on all 5 bottles. And then we want to find the probability he wins on at least 1 bottle. And last time I wrote too big, so I'm going to draw a line so I stay in the right spot, because then things were running into each other and it did not look pretty. All right, so we want to find the probability that he wins on all 5 bottles. Probability win on all 5. So the probability that he wins on all 5 would come from the probability that he wins on the first bottle, and he wins on the second bottle, and he wins on the third, and he wins on the fourth, and he wins on the 5th. That would give us the probability that he won on all 5. Now it tells us that we can assume each bottle is independent. And the other day we learned a rule for independent events. And that rule was that the probability of A and B comes from the probability of A times the probability of B. So, oops, sorry, I'm off the screen a little, there we go. So we can take that rule for independent events and we can apply it here because we're told that each bottle is independent. So the probability that he wins on 1 and wins the second and wins on the third and wins on the fourth and wins on the 5th can be found by taking the probability that he wins on the first. Yes, Chloe.
Taylor said her internet broke and she's going to watch the notes.
Sure. Okay. Thank you for letting me know. Wins on the 3rd times the probability he wins on the 4th times the probability he wins on the 5th. You know what I just thought of, Chloe? When she watches the notes, she's going to hear me say, sure, her internet broke.
Hi, Taylor. Hope you're watching the notes.
All right. And in the paragraph, it also tells us that the probability of winning is 1/6 for each. So 1/6 times 1/6 times 1/6 times 1/6 times 1/6, or if you're an exponent person, which I am, you can use 1/6 to the 5th power to find this. Okay, so last time we talked about the multiplication rule for independent events, and we looked at, remember, the pitcher throwing a perfect game, which really was throwing 9 perfect innings. And then the other one was the World War II bomber coming home from his mission safe. So this is just like that. And if we plug this into the calculator, we get, ooh, sorry, glare's right on there, 0.000129 with rounding. So he has a really small probability that he's going to win on all 5 bottles that he bought. So that one's just review of our independent rule. Get our brains back into math gear. Now I'm going to introduce how to use one of our previous rules in a new way. So we want to find the probability that he wins on at least 1 bottle. Now, what does that phrase actually mean? He bought 5 bottles. What does it mean when we say wins on at least 1 bottle? What does that mean?
It means that he wins on 1 or more.
Thanks, Piper. Means that he wins on 1 or more. So he could win on just 1 bottle. He could win, 2 of the bottles could be winners. He could have 4 of them be winners. He could have all 5, or he could have 3 be winners. So this means 1 or more. And for whatever reason, at least and at most tend to be the most misunderstood inequality phrases. So 1 or more winners. So every year I have kids that go, okay, probability that this guy wins on at least 1, which by the way I'm using my greater than or equal to 1 because we can have 1 or more winners. I just don't want to have to write at least 1 each time. Every year I have kids go, okay, probability that we win on at least 1, that comes from the probability he wins on 1, plus the probability that 2 of them are winners, plus the probability that 3 of them win, plus the probability that 4 of them win, and then plus the probability that 5 win. Oops, I forgot my P. That is not true. It's a good starting point, but those are not equal to one another, okay? And here, let's say that Mr. Wilcox numbered his bottles 1, 2, 3, 4, and 5. And we're just going to focus on 1 of those bottles being a winner, just 1. The winner could be the first bottle, and then the rest were losers. Or the first one he opened was a loser, and the second one was winner, and the rest are losers. Or the first 2 are losers, the third one's the winner, and the rest are losers. Or the fourth one's the winner, and the rest are losers. Or the first 4 are losers, and the last one's winner. So there's 5 different ways that he could win on 1 bottle. And you would have to multiply 5 by that. Now, if we're looking for 2 winners, there's more ways because the first and the second, the first and third, first and fourth, first and the fifth, there's actually 10 different ways you could have 2 winners. And yeah, you could go through and figure out, I don't remember on 3. I feel like it's also 10, but my brain is not working the best today. But I'm pretty sure it's 10 ways that you could have 3 winners, and here it's also 5 ways. And then this one, there's only 1 way all 5 could be winners. But kids forget to multiply by that. Plus, in a minute, we're going to look at 100, a sample size of 100. And then on the back, we're going to look at a sample size of 200. And there's no way you want to do that. When it's a sample size of 5, like it is here, you could theoretically go through and figure all of that out, But the at least one is a shortcut. And so that is what we're going to focus on today. We're going to learn how to find the probability of at least one. And the way we're going to think about it is with the probability of at least one, Piper told us that meant one or more. The only situation that doesn't cover is if we have 0 winners. So we're going to think about the complement here. So the probability of at least one complement would be the probability of no winners. Everybody agree with that statement? The complement of at least one is no wins. At least one winner, complement, no wins. Everybody agree with that statement? Okay. So we can use our complement rule when it comes to being asked to find the probability of at least one. So the complement rule, remember, tells us that the probability of a complement is equal to 1 minus the probability of A. We're going to manipulate it a little bit because we want to find the probability of at least one. So we're going to do 1 minus the probability of at least one complement or having no win. We could show that part, but trust me, this follows that rule. Now, the weird thing about the probability that there are no wins is that it's a complement rule in itself. So the probability of no wins is the same as the probability of losing to the 5th power. Because I have 5 bottles, all of them are no wins, so I'm going to raise it to the 5th power because we're told we can assume independence. But I have to use the probability that the bottle is a loser, not a winner. And the probability the bottle is a loser comes from 1 minus the probability the bottle won, or is a winner, which we're told the probability of winning is 1/6. So the probability that it's a loser is 5 out of 6. So the probability of no wins is 5/6 to the 5th. So the probability that he wins on at least one bottle comes from 1 minus the probability of no wins, which we find by taking 5/6 to the 5th power. Five, 6 to the 5th. Should probably put that where you can see it. And then 1 minus that. So the probability that he wins on at least one is 0.598, which is actually a pretty good probability. It's about 60%. Questions? No? All right. We're going to look at another one, actually another 2, where we use that at least one idea. So this one, the first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a positive result. If 100 women with normal pregnancies are tested with the first trimester screen, what's the probability that at least one woman will receive a positive result? So probability of at least one woman is going to come from 1 minus the probability that none of them get that positive test. So remember, the probability that none of them get a positive result is a complement rule in itself. So the probability of none is equal to the probability that they all get negatives, because it's what's the probability at least one gets a positive result. So none of them get a positive means they all get negatives, and there are 100 of them. Now we're told here that 5% get a positive result. So the probability of positive is 0.05, which means that the probability of negative comes from 1 minus 0.05, or 0.95. So the probability that none of the women get a positive result would be the probability that they get a negative to the 100th power, because we're looking at 100 women. So we would have 1 minus 0.95 to the 100th power. And then 1 minus that. So we get 0.994. So the probability that at least one woman would get a positive result on that first trimester screen is about 99.5%. Questions on that one? No? Alrighty. Excuse me. Alright, last one we're going to look at. So many people who come to clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn the test results. Clinics now use rapid HIV tests that give a result while the client waits. I'm going to say this country's name incorrectly, sorry. In a clinic in Malawi, my husband would be so furious. He's world studies. He'd be like, why can't you say that? I don't know why I can't say that one. So in a clinic in Malawi, the use of rapid tests increased the percent of clients who learned their test results from 69% to 99.7%. The trade-off for fast results is that rapid tests are less accurate than slower laboratory results. Applied to people who have no HIV antibodies, one rapid test has probability about 0.004 of producing a false positive, so falsely indicating antibodies are present. So if the clinic tests 200 randomly selected people who are free of HIV antibodies, what's the probability that at least one false positive will occur? So probability of at least one false positive. We're going to take 1 minus the probability of no false positives. So, sorry, I'm trying to think where I want to do my side work. So the probability of no false positives, I guess for lack of better words, would come from doing sorry, I don't know why I wanted to change it to true positives. It comes from 1 minus this. So I guess what you're finding is how many true positives. I guess that's where my brain was going. We're taking 1 minus that, and that'll tell us the probability that we get a real positive result, which would be equal there, 0.996. And then because we want none of them to be false positives, and we're looking at 200 people, we're going to raise it to the 200th power. So we have 0.996 raised to the 200th. And 1 minus that. So the probability that we get at least one false positive is about 55%. That's really high. Questions on that one? That is all that I have for notes for today. Remember